Assalamualaikum and hello everyone. In this video, I will be presenting my case study, the technical review on FK filter, stand for frequency with number filter, which also known as velocity filter. My name is Nolili, and this is my presentation for QBB 4033, Seismic Data Processing in semester January 2021. The abstract for the overall presentation. FK filter is one of the important methods in seismic data processing applied in order to gain the best seismic image with only reflected signal from the seismic sources, without unwanted signal such as noises and other waves. The filter, applied after seismic signal separated into two components of frequency and wave number, able to attenuate the noise after selecting the filtering range to a certain value. Even though the method is known to be applied on the preset data, there were some people who indeed tried to experiment on applying the method to the different type of data, such as 3D processor seismic image. Some find good result, while others could only compare the methods. There are several issues on the method itself regarding its genuineness on the success and the process and the application of the methods that we can discuss. While comparing different research papers on the topic, various interesting findings are found and yet to be explored. To get started, we need to know and understand FK filter first. In general, in seismic data processing, FK filter, the frequency wave number filter, is a two-dimensional filter mainly used to attenuate the unwanted signal, especially the coherent linear ground rule and noises. FK filter is a continuation process after the frequency filter, which also known as velocity filter. Basically, in seismic data, velocity is a really important parameter in order to get the best seismic image for further analysis and interpretation. In fact, a lot of noises in subsurface data related to the velocity. Through FK filter, we transform the time-space domain of the seismic data through the integration in respect to both time and space into frequency wave number domain to make the identification of the signals and noises more visible and clearer. After the transformation, we will be able to separate between the low and high frequency and the wave number of the components of the acquired seismic. That is how we are going to target on the low frequency component of the noises to be attenuated. After the process is done, we will transform the FK domain of the current data back to the time-space domain. FK filter mostly done to the short gather or preset data, but it doesn't mean that it cannot be applied on the other data, which we will discuss about later on. To summarize the review on the research papers, the objective of this presentation are: we're going to study on the FK filter and its mechanism. Second, we're going to take a look on its advantages and the new finding on the method. Third, we will see if there is any limitation or issues with this application. Then, we will talk about the direction of this process or method in the future. So, what is FK filter and how does it work? Let's go through the process first. In beginning, we have the original seismic data in the time-space domain. So first of all, we use the information stored in the header and its structure to obtain and manipulate any information. Second, we transform the time-space data into frequency wave number domain to separate the two components of the signal that were captured in our seismic. Then, we conduct the FK filter according to the value that we set. After that, we do some Q compensation or we gain the energy and amplitude that lost due to the previous process. And now that we are satisfied on the outcome, we can transform the data into the time-space domain back. So, why did we transform the time-space domain of our data into frequency wave number domain in the first place? In the time or space domain, their dimension is controlled by the trace spacing, and according to the Nyquist theorem, The sampling frequency must be at least twice the signal frequency, up to the Nyquist frequency to avoid aliasing. As we all know, frequency is the number of cycles per second. For spatial frequency of wave number, k, it is the number of cycles per unit distance, while spatial wavelength is equal to 1 over k. There is another important parameter which is d, second per unit distance, which equal to k over f multiplies with the trace interval. So, d is the one cycle of the time frequency in a distance equal to one cycle of horizontal frequency. In the FK domain, some events are with different frequency. We have the same d corresponding to their wave number. That is how we will be able to separate two or more different signals. Each straight line event, like a direct wave, reflected wave, or surface wave, has a particular apparent velocity. However, a reflection event shows as a curved hyperbola on the original section. When we have nonlinear or hyperbolic signal, which is more likely in real life, we tend to have background noises, which are practically artifacts and hinder our data. We must not have too narrow bandwidth or short boundaries to avoid the problems. This is where the band reject zone must be extended to Nyquist frequency to preserve all frequencies. Although it was more computationally extensive compared to the frequency filtering, this method of FK filter allowed the elimination of the coherent noise without reducing the frequency content of the seismic data. This method also gave better results as we can now identify the coherent noise and therefore give a better noise attenuation without damaging the primary signal. However, this technique is applied on the preset seismic data for the optimum result. Now, there is this one interesting paper, an old research paper by Robert R. Stewart and David G. Schreck, focusing on applying 3D FK filter not to the preset data, but the post-stat seismic image itself. In this research, they tried to design and use three-dimensional FK filter on the post-stat data volume. At the end of the filter application, they compared the result from the both preset and post-stat FK filter. The reason why they did this because they claimed that the FK filter on the preset data could not be able to completely eliminate the unwanted signal. Then, giving the specific velocity or deep reject range, they observed different response on the basic 2-pass 2D filter and 1-pass 3D filter that they applied to the data. In fact, they said that the 2-pass filter do not provide axially symmetric result, while the 1-pass 3D filter does provide axially symmetric result. At depths greater than 45 degrees past to the filtering direction in the post-stat data, they also compare a mean and median implementation of the 3D FK filter. It turned out the application of the mean filter resulted in a more smooth image than the median-based filter. However, when there are structures such as fault that needed to be preserved, or where the data are particularly noisy, the use of the median-based filter was suggested and more suitable to be applied. It seems like where the 2D FK filter highly recommended and used by most people, the 3D filter is yet to be fully developed to be applied on the post-stat data, especially mainly due to its possibility to affect the amplitude of the state data. However, Roberts and David had attempted this method and recommended them for migrating diffraction. Referring to the result presented by both of them, the 3D median concept of FK filter does reduce the noise effectively without smearing the other anomalies of important events. Regardless of this old discovery, there was a recent paper around 10 years ago by Matthew Revesi and others saying that they applied the FK filter to both pre and post image of the extended data to find out that the hyperbolic move out is present at low wave number and is fairly distinct from physical energy in preset data. And post-imaging filter limiting dips also produce a reasonable extended image as displayed. In this paper by Revesi and his colleagues, they applied the FK filter to both preset and posted data and agreed that just like how the hyperbolic move out is present at low wave number and is fairly distinct in preset data, the post-imaging filter limiting dips also display a reasonable result. However, note that the pre-imaging filter has suppressed more energy due to external sources in the source correlation gather than has the post-imaging filter in the source correlation gather. Similarly, the energy near the critical angle is weaker in the pre-imaging FKF spectrum than in the post-imaging one. Hence, this filter could provide fairly different results for situations where the physical stationary points are due to sources at the edge of the boundary. Now we look at the topic. There are several issues that perhaps we can think about. First, some seismic data were acquired in a high resolution using a high frequency sources, which resulted in a much higher level of noise that can come from various sources, be it the scattered noise, guided wave, cable noise, ship propeller, and even the multipliers that could be even more dominant than seismic signals themselves. So, in order to remove only the unwanted signal, the proper noise removal technique must be chosen to eliminate this noise while preserving the frequency bandwidth of the seismic data. Second, we acknowledge that FA filter only applicable with posted data. So what about the previous posted attempt by Robert and David that claim they successfully to completely remove the noises without affecting the seismic data? Next, while zero offset data commonly used in shallow marine survey to observe the subsurface, it is difficult to apply this technique into zero offset seismic data. But it is not impossible to make it work if we found the correct processing workflow, isn't it? In conclusion, FK filter is a filtering method where we convert the time-space domain of our signal into frequency wave number domains in order to eliminate the unwanted signal that falls within certain range of frequency or wave number. It is mostly applicable in short gathers in preset data, with some attempt on the posted data that could be effective. Despite of its ability to remove the unwanted signal as we design our processing flow, there are still some rooms of improvement that many nature scientists or geophysicists maybe will try to develop to make the method work even wonder. Now, it is interesting to ponder about the future of active filter seismic data processing. As mentioned before, perhaps with more research, active filter would work wonderfully against posted data or even seismic image itself. Or perhaps future active filter will not cause much energy or amplitude loss to the data, meaning that less work to gain the processor's data. And it will be applicable to more offset data. With advanced technology that the work becomes smarter, the processing method also becomes less time consuming and less complex. Now, I thank you for watching this video. Thank you and Assalamualaikum.